All right, so here is a second order, what? Second order
Linear homogeneous differential.
linear homogeneous differential equation with, I didn't teach you these words. What's special about the coefficients on this one? They're constants. So if they're constants, your quadratic formula thing is definitely more likely to work. Does that make sense?
Yeah.
Like if your friction depends on the time, or your spring decay, like your spring gets less springy over time, then you got problems. Right? So if these are constants, you're good to go with that idea of, what was my idea?
Y equals e to the RT.
Okay, you guess y is e to the RT.
Skipping those steps, just r squared instead of y prime, r instead of y prime, and
Okay, perfect. So you got r squared plus 2r minus 1 equals 0. This thing is called the auxiliary equation. Why is it called the auxiliary equation? Because it's the other equation you need to solve.
So if we have constant coefficients, we can just convert straight, like pretend that's a quadratic and like take
Totally.
the double prime and it's a squared and then the prime.
Yeah, so the interesting thing, like the thing I don't want you to forget, is like do this flip. Yeah, straight up. The powers of the derivative, or the number of derivatives you've got turns into powers of r. But remember that when you're done, you need to plug that back into e to the RT to get your answers. You guys cool with that? So I got this, which I might spend a second and like try to solve for r. So when you're solving quadratics, what should you do? Sure, you could complete the square, or you could use the quadratic formula, or you could factor and then use the zero product rule. I give no poops which of those you do. Okay? Well, whatever's easiest for you. I'm going to go with Chris's suggestion because I thought that was a good idea. I'm going to add 2 to this side, and I'm going to add 2 to that side. And then this is r plus 1 squared. Is that not how you complete the square, Chris?
I would add 1 both sides.
Yeah, you'd move the 1 over first and then do
Now
that.
that's the same thing.
However you complete the square, my method's never been very consistent. It depends on my mood, apparently. That was actually one thing I learned teaching Algebra 2 here, was that you have to have a consistent method to complete the square. You can't just do whatever to get it done. Because when I tried teaching the do whatever to get it done, it was not good. I ruined a whole class of students. Felt bad. So what do I get at the end here? What's your next step?
Square.
Yeah.
Yeah, make sure you get both bits. You'll need them both. So you get plus or minus square root. So you get r plus 1 is plus or minus the square root of 2. And then knock the 1 to the other side, so you get r is negative 1 plus or minus the square root of 2. Right? And so then you arrive at the fundamental confusion of second order differential equations, which is you now have 2 possible solutions. You have y1 is e to the negative 1 plus the square root of 2, and y2 is e to the negative 1 minus the square root of 2.
And those are multiplied by whatever your independent variable is.
T.
Yeah, it's both times e x, whichever x you want to specify.
Yeah.
Thank you. So I have e to the minus 1 plus root 2t and e to the minus 1 minus root 2t.
Does this kind of imply that if you have a third order, you get 3 possible solutions?
It does, yeah. So you'll get some bits. Now the funny thing about the bits here is is you need to account for a general solution, right? That thing solves your differential equation. That thing also solves your differential equation. So the fundamental solution set is these two things. So the general solution is C times this first thing, maybe C1, e to the minus 1 plus the square root of 2t plus C2 e to the minus 1 minus the square root of 2t. This is what your whole y is.
Are we actually adding them, or are we doing a union or something?
We're actually adding them for reasons. The differential operator, right, the ddx, is linear across addition. It's not linear across multiplication. So it turns out that this is the good idea. Okay, now, sometimes you'll end up with two solutions and you won't be sure that they're independent. Right, like in the case where you have repeated roots over here. Right, like if you got r plus 1 squared equals 0, then you'd be like, but they're the same? So what now? Right? And so the what now is a little bit beyond, but yeah, you kind of tack something extra on. The thing I want to give you guys before we're done for the day is a Wronskian. So when you have two solutions like this, there's a thing called a Wronskian that's a function of two functions.
Yeah.
And the way you calculate that is you take y1, y2 prime minus y2, y1 prime. And let me look and make sure I got the order the same as it is in your book so that you're not confused. Where'd my thing go? y1, y2 prime? Okay, so you will need to calculate some Wronskians in your homework. I don't expect you to actually use them for anything right now. I want you to know that this exists and that it's a tool for checking the independence of solutions.
Is that also like a
Cool.
square matrix full of derivatives?
Yeah, there's a way to think of it as a square matrix with some derivatives. Cool? Questions? I'm not actually telling you what to use this for. I just want you to be able to calculate it for practice if we can.
So,
Anything else?
what are the other questions?